Hi everyone, this video is about formal logic. Up to this point, your experience in math has probably been largely computational. You've had teachers who've asked you to do various things like factor polynomials or compute an integral or compute a derivative, maybe solve a related rates problem. It turns out, though, that there's a lot more to mathematics than computation. In fact, sort of the main goal of mathematics is to understand and develop statements about mathematics and determine whether they are true or false. So for instance, there is a statement in calculus that says that every continuous function on a closed interval is Riemann integrable. And we can't just walk away from that statement. We would like to know whether it's true or false. It turns out that it's true, and it's not enough for someone just to declare that it's true. We want a true statement like that to be paired with an argument, an airtight argument, which we call a proof, that would convince you and me and all of the reasonable world that that statement is true. So in this course, one of the purposes, one of our goals, is to learn something about mathematical proof. So formal logic is a means by which we can begin to understand the ideas involved in mathematical proof. So formal logic allows us to evaluate the truth of certain statements by manipulating symbols according to well-defined rules. So one advantage of encoding statements in terms of symbols is that it can help us understand some highly complex statements. One example of a highly complex statement is the definition of the limit from calculus. So as I was mentioning a little bit earlier, formal logic is directly applicable to mathematical proof. That is, this idea of providing a justification of a true mathematical statement. And further, formal logic is good for our habits of mind when producing mathematical proofs. In the next couple of slides, we're going to be talking about some of the components of formal logic. So first, a statement is a declarative sentence that is either true or false, but not both. So here we have several examples of sentences, and we're going to determine whether they're statements. So the first is that 2020 was an election year in the United States. I think we will all agree that that is a statement, and in fact, it's a true statement. Now, in the second bullet point, we have this command, go fishing. Well, there's nothing really declarative about that. It's just telling us to go fishing. And no matter how much we would like to go fishing, we can't say that this is a statement. Right, so this is not a statement. Next, we have, if Jim wins his next tennis match, then he'll be in the semifinals. Well, that's something that's true or false. It's a declarative sentence. And so this is a statement as well. In fact, it's a special type of statement called a conditional statement. It's something that involves an if and then a then. Right, so it would be unjust, for instance, if Jim really did win his next tennis match and he didn't go to the semifinals, then that would be a real problem. And we'll talk about that a little bit later. Okay, and then next we have this question, are you related to Bill Gates? Well, maybe I wish I were related to Bill Gates, but, this is not a declarative sentence. So this is not a statement. Okay, now the next one is sort of interesting. There is life on Mars. Okay, that's a declarative sentence. It's either true or false. Now, we don't know whether it's true or false, whether there is life on Mars, but this doesn't stop this from being a statement. It is a declarative sentence. It's either true or false, and whether we know it's true or know it's false has no bearing on whether it's a statement. And then finally, we have this wacky sentence at the bottom, saying this sentence is false. Well, this is sort of a conundrum because, if that's true, then how can the sentence be false? If the sentence is false, then it should say this sentence is true. So things like this where it's not clear, it seems declarative, but it's hard for us to determine, whether this is either true or false, but not both. And so we determine that this is not a statement. One thing we can do with statements is put them together using logical connectives to make more complex statements. So there are several logical connectives that we'd like to discuss here. So first of all, we're starting with some given statements, P and Q. Okay, so they're just statements, declarative sentences that are either true or false, but not both. So one thing we could do is talk about P or Q, which is denoted by this wedge symbol. So that's P or Q. We could also form P and Q, right, which is indicated by this tent symbol. And then we could form the opposite of a given statement, right? So not Q, it's given here. And then here the P arrow Q is our conditional statement, if P then Q. And then finally we have the double-sided arrow, which means P if and only if Q. All right, so how do these connectives play out in a specific example? Well, let's let P be the statement, Jim hates asparagus. And Q will be the statement, Jane likes chocolate. Then not Q, evidently, is Jane does not like chocolate. And then here, P tent Q, that means P and Q, so that's Jim hates asparagus and Jane likes chocolate. Now in the third bullet point, we have something a bit more complex. So this is if not Q, then P. So this would be if Jane doesn't like chocolate, then Jim hates asparagus. And then finally, in this fourth bullet point, we have the opposite of if Q, then P. So that would be the opposite of if Jane likes chocolate, then Jim hates asparagus. And, that's a rather clunky way to phrase that, the opposite of, Jane likes chocolate. If Jane likes chocolate, then Jim hates asparagus. So you might think about, what might be a better or more concise way to phrase that statement? If we have a statement that depends on existing statements P and Q, we can determine whether that statement is true or false by forming what we call a truth table involving the truth values of P and Q. Now, on the previous slide, we had these common logical connectives that form statements from existing statements P and Q. So why don't we give truth tables for those statements? So first, why don't we look at P or Q? Right, so remember, the P or Q is denoted by this wedge symbol here. Okay, so first we look at all of the possible truth values of P and Q. So it could be that both P and Q are true, or P is true and Q is false, or maybe P is false and Q is true. And the other possibility is that they're both false. So there are no other possibilities for P and Q. Now for P or Q, what we're going to require for that to be true is that at least one of P or Q has to be true. So that's certainly the case here. In fact, both P and Q are true. Now in the next two lines, P is true, so that's enough to make P or Q true. And then in the next line, Q is true. In fact, the only way P or Q can be a false statement is if neither P nor Q is true. So that happens here. So P or Q is a statement that wants to be true almost all the time, right? There's just one instance where it's false, and that's when both P and Q are false. So why don't we also then look at P and Q. In fact, maybe we should just extend this table here. So let's look at P and Q. So for P and Q, for that to be true, we want both P and Q to be true. And the only way that happens is in this first instance, right, where both P and Q are true. Everywhere else, at least one of P and Q is false. So the and corresponding and statement will be false as well. Why don't we go for the negative statement now? How about not P? Right? So not P will be false whenever P is true. And it will be true whenever P is false. Okay, that seems reasonable. Okay, now we come to this conditional statement, if P then Q. All right, what are the truth values of that statement? How do they depend on P and Q? So for this, I would urge you to think of this conditional statement, if P then Q. Right, which in notation is this arrow, right? I'd urge you to think of this as sort of a promise that's made. Right, like for instance, if my son cleans his room, then I will take him out for ice cream. Right? The only injustice, the only way a really bad injustice can take place is if my son cleans his room and then I fail to take him out for ice cream. So here, let's just look and see if any sort of injustice, as we go down through these truth values of P and Q, let's see if an injustice has occurred. If there's an injustice, then the conditional statement will be false. Otherwise, it will be true. So here, again, we can maybe think of P as being my son cleans his room, and Q being I take him out for ice cream. So in the first instance right here, both P and Q are true, meaning that my son does clean his room, and then I follow through and take him out for ice cream. And so since that promise has not been broken, we declare the conditional statement, if P then Q, to be true. So now in the next line, my son cleans his room, but I do not take him out for ice cream like I had promised to do. And in that instance, the promise has been broken, and we declare the conditional statement to be false. Okay, now in the third and fourth cases, my son fails in both cases to clean his room. And if that's the case, whenever P is false, then this conclusion, Q, whatever it is, there's no injustice that has occurred. Like, I could decide anyway to take him out for ice cream. That's totally fine. Or I could decide not to take him out because he has failed to clean his room. So notice that the if P then Q statement here and the or statement, they are both wanting to be true a lot of the time. In fact, the only way a conditional statement can be true is if the first part, P, is true, and the second part, Q, is false. Okay, now there's one more logical connective for us to deal with, and that's the P if and only if Q. So that's the two-sided arrow there. Now here, for this to be true, what we're looking for is that P and Q have the same truth values, right? So in the top case, P and Q are both true. They have the same truth values. In the next two cases, P and Q have opposite truth values. And then in the bottom, P and Q are both false. They have the same truth values, so the if and only if statement is true. Okay, so you can think about this statement as being true exactly when P and Q have the same truth value. Either they're both true or they're both false. Otherwise, the if and only if statement is false. So two statements are logically equivalent if they have the same truth values. And on this slide, we're going to do an example where we explore the idea of logical equivalence. So P is the statement, you're in London. Q is the statement, you're in England. And the question presents us with three statements and asks whether each of them appear to be logically equivalent to the statement, if P, then Q. So now, if P, then Q says, if you're in London, then you're in England. This first statement, if Q, then P, says, if you're in England, then you're in London. So that does not quite appear to be the same thing as if P, then Q. Now the second statement says, well, if you're not in England, then you're not in London. And if you think about it for a little bit, that does seem to be pretty similar to the statement, if you're in London, then you're in England. And then finally, we have the statement, not P or Q, which says you're not in London or you're in England. Is that logically equivalent to if you're in London, then you're in England? And maybe that's a little bit harder to tell just on the face of it. But the good news is that regardless of the statements what the statements P and Q are, we can resolve this issue using a truth table. So let's do that here. So we have statements P and Q. And then we have this bunch of other statements, right? We've got if P, then Q, which is the statement that we're comparing to some of these other statements. And then we have if Q, then P. And then we have if not Q, then not P. And then we have not P or Q. Okay, so now the first thing we should do is write down the possible truth values of P and Q. So they could both be true, P could be true and Q could be false. P could be false and Q could be true. Or they could both be false. Now, you might object to this second possibility, right? Because how in the world could you be in London when you're not in England? And what I would urge you to do is to consider this option anyway, because we want whatever we say to apply to any statements P and Q, not just the ones that were given in this example. So I realize that this second option seems absurd, but let's go ahead and keep it because it may find applicability with other statements P and Q. All right, so let's go and produce truth values for all of these other things, all of these other statements. And we're going to want to keep track of which of these columns match the column that we get for if P then Q. So you might recall from the previous slides that the truth values for if P then Q are as follows. Right? The only way the conditional statement if P then Q can be false is if P is true and Q is false. All right, so now to test logical equivalence, we're looking for the same collection of truth values. So that means that in these next three statements, I'm going to produce a column of, in each one of them, I'll produce a column of T's and F's, and I want to just make sure or check whether that column of T's, that column of T's and F's matches the column of T's and F's in the conditional statement. So let's look at if Q then P. So now remember, the only way that that can be false is when Q is true and P is false. So that happens here. And everywhere else, if Q then P is going to be true. So now I compare that column of T's and F's to the column of T's and F's in the conditional statement if P then Q, and I compare them, and I see that they don't match up, right? So this is not logically equivalent to if P then Q. All right, now we have this next statement, if not Q, then not P. So remember, that's a conditional statement, and the only way it can be false is if not Q is true and not P is false. So not Q being true and not P being false would only happen in this second row, right? Not Q would be true, not P would be false. And so the conditional statement in total is false, and everywhere else it's true. So now we compare that column with the conditional statement if P then Q, and we see that the truth values match up exactly. And so that statement is logically equivalent to if P then Q. And in fact, it has a name. It's called the contrapositive. It's called the contrapositive of the original conditional statement. So we're going to see down the road that this idea of the contrapositive can be useful sometimes when one is attempting to prove theorems in mathematics. All right, now what about this last statement that we were a little bit concerned about? All right, so remember, this is an or statement, and an or statement will be true when at least one of the component statements is true. So here, in the first line, I know that Q is true, and so not P or Q is forced to be true. Now in the second line, Q is false, not P is also false, so both component statements are false, and that forces the or statement to be false. Now in the third row, Q is true, so the or statement is automatically true. And then finally, in the fourth line, both P and Q are false. That means that not P is true, and that forces the or statement to be true. And now I compare my column of truth values with the implication, if P then Q, and I notice that it's a perfect match. And so this statement also is equivalent to if P then Q. Maybe rather surprisingly, it is equivalent.